Okay, good afternoon for everybody. So let us go on. What I want to do today is a little bit change the subject and first come to say to less formal aspect of mathematical proof, and again look into some classical examples as we did in the very beginning of our course. And then, if time allows, we will come to a different formalism, but that is called lambda calculus. You can look into our syllabus, it's there. But I want somehow motivate this lambda calculus and why it's interesting and important for when we talk about mathematical proof. So first thing, I somehow assume we started rather thoroughly the natural deduction system, and actually both for classical and for constructive logic. So I hope I somehow showed you the difference and demonstrated it with some examples. So I'll just stop at that point. There are, of course, further important developments. Some of these developments were already started by Gerhard Gentzen himself, who I remind you is the inventor of this natural deduction system. And it's actually called, I can just give you title, it's called sequence calculus. So it's kind of different formalism that allows to make more control on natural deductions, right? Remember, in natural deductions, we have hypotheses or assumptions, some of which are discharged, right? And that actually, no, I think it works well intuitively if you have some experience. However, you may want to have more kind of written control, what is going on really, to put more things on paper, and basically that's what this sequence calculus achieves. And of course, it's also very important if we talk about further, say, theoretical proof theory. However, my goal is not to really go too far, say, theoretically, but not also not to leave this kind of practical aspect, right? We should somehow always keep in mind that we want to apply this theory for representing certain proofs, right? In mathematics and also probably outside mathematics. So I want now come back to actually very classical example that I think I also mentioned already in the beginning, and that's actually was example of Euclid's elements. Sorry, it's not what I want. Okay, I stopped my video. I should change my PDF, sorry. Yeah, this is, can you see Euclid's elements of geometry?
Yes. Yes.
Okay, perfect. Yeah, I already, I think, mentioned that that is a very old source, which actually serves for many years as a, say, inspiration and actually as a textbook for developing mathematics for many, many centuries. And actually also via certain upgrades and transformations. So that should not be understood that people just looked into what Euclid wrote. And Euclid lived in 3rd century before Christ, right? Like minus 3rd century. And here you have a actually attempt of reconstruction of how the text he wrote actually looked like, and as people somehow close to humanities, right? Not only to mathematics. You should, of course, understand that this is only approximation, because history, and moreover history of text, is actually quite a, how say, it's complicated discipline, complicated in the sense that you need really a lot of efforts to achieve certain, say, plausibility, right? Plausibility of claims that say what we are going to see now, it's really what Euclid wrote, more or less. And of course, it's like in natural sciences, by the way. We should understand that that goal simply cannot be achieved in some precise sense. So you should not, or cannot even expect kind of symbol by symbol, word by word identity. It's all reconstructed through, say, some extant texts or manuscripts, and there is a lot of philological work and say historical argumentation behind it. But that's something that we don't go into. That's basically, this work was done by German philologist, forgot his first, Joachim, I think his first name, Joachim Leonard, if I'm not confusing, Heiberg, who you see lived back in the 19th century. And since then, there were some improvements and, say, challenges to his work. However, this still remains quite a standard reference, this source. And this particular translation is made into English, actually by an amateur, a person who is a professor in quantum physics, but he also spends a lot of time on working ancient texts and actually does it really professionally. His name is Richard Fitzpatrick. No, actually, this English translation is not very different from another English translation, which was actually made in the beginning of 20th century by Thomas Little Heath. That was first translator of Euclid's Elements from this hybrid version of the text into modern English. So here are some updates, but it's rather, they just reflect some changes in the language rather than some important sort of revisions. No, anyway, yeah, by the way, Euclid also exists in Russian, and that's a translation. I can try to write you down, just that by any chance you may be interested, you can. Да, давайте уже про русский скажу вам по-русски. Сейчас, одну секунду, доставлю свой планшет. По-русски это называется «Начало Евклида». Ну, кстати, довольно забавно, что у нас вот в русском языке такое название «Начало Евклида». Elements по-английски это, ну, как калька латинского перевода, который читается как элемента. А по-гречески это, по-моему, пишется вот как-то так, как архай. Ну, от этого слова археология, например, происходит, да, вот какие-то базовые первичные элементы. Oh, no. I'm really sorry. I confused. It's not archai. It's, yeah, archai is another word, which is somehow close. No, it's called stoicheia. Stoicheia. Stoicheion, stoicheia. And stoicheia, это слово, кстати, используется тоже для букв алфавита, да, то есть это также переводится более-менее как алфавит, то есть вот первичные элементы как бы буквы. Ну, кстати, в этом значении, почему начало, у нас есть слово русское стихи, которое тоже этимологически восходит к вот этому стихе. Как это точно получилось, ну, где-то описано, но я сейчас точно не помню. Вот. У нас начало Евклида, и переводчик Евклида, еще раз я говорю про переводчик, я сейчас имею в виду вот именно перевод с этой версии, ну, которая более-менее приближена к оригиналу, по крайней мере, вот была серьезная филологическая работа и аргументация в попытке сделать вот как бы такой текст, восстановить его, поскольку есть и другие более ранние переводы, но они вообще на самом деле не с Евклида, то есть они к Евклиду такое имеют отдаленное отношение. Вот. И по-русски переводчик, его зовут Дмитрий Дмитриевич Мордухай-Болтовской. Такой вот был математик, очень интересный. Я, кстати, когда-то издал еще такой сборник его трудов там, по истории математики, но еще про разные вещи. Так что можете поискать по Гуглу и найдете, если вам интересно. Вот, так что у нас вот на русском языке один есть такой перевод, Болтовской. Он был сделан во время войны, там, ну, это в нем 13 глав, которые называются книгами. Это существует на русском языке в 3 томах, это издание. По-моему, последнее вышло в 50-м году, если не ошибаюсь. Но опять-таки просто погуглите начало Евклида, Мордухай-Болтовской. Ну, все эти тексты тоже можно сейчас найти в интернете, если вам будет интересно. Окей. Okay, so I go back to Euclid. Yeah, probably I should say why Euclid. It sounds like some very old mathematics, historical mathematics, right? But the thing is that kind of form of this, of course, the content of this mathematical content is a kind of outdated. It's still used in a school education, but probably now less than say several decades ago when I was in school. So I think it's less and less. However, some very, how to say, form of mathematical reasoning, it's still very, very much alive, even in today's mathematics. It's, of course, there's a rather strong claim and needs a special argumentation. You can find it also in my book. Now I will not stop on that, but so it's just for justifying the idea that looking in Euclid, we still can read off it some important feature of say mathematical reasoning, mathematical proof, more specifically, which is still very much alive in mathematical practice. And on the other hand, it's not so much and so well reflected in, say, logic, in proof theory. And that's exactly why I'm coming back to Euclid. Okay, let me just see. So I recall you that it begins with a rather long list of definitions, which are kind of interesting, and they're very unlike today's mathematical definitions, because today people rather regard definitions as some technical gadget or instrument, right, that just allows you to introduce a new term. Instead of giving some long description, you just call it by one word, something like this. And some of Euclid definitions, they are like this, right? That's something like definition of circle, for example. It's 15. Circle is a plane figure contained by a single line, such that all of the straight lines that is radiating towards this line, which is called this circumference, окружность по-русски, да, круг и окружность, from a single point lying inside the figure, and this point is called the center. And that's so yeah, you can see kind of description of what is circle in this definition. However, if you look, for example, first definition, that of point, you see a point is that of which there is no part, right? So it basically says that is an atom, something which is indivisible. And yeah, it could be used as a property, but also the fact is that it nowhere in the following proof it's used, right? It's kind of assumed. It gives you intuitive idea of what is a point. However, this property that it has no part, right, that it is indivisible, it nowhere used in the definition. So for that reason, today people would say this definition is useless, or at least it doesn't work as a, say, mathematical definition. It works as a kind of description which may have some pedagogical value, right, but not as a mathematical definition. But no, anyway, let me skip definitions. That's interesting, this system. I basically made my dissertation about these definitions mostly. But let's see two further sets of principles, right? And the next set of principles called postulates, yeah, postulate, aithemata in Greek. And let us look a little bit more precisely into these postulates, because they are really important for what I want to demonstrate. Let it have been postulated to draw a straight line from any point to any point. Now, basically, it says what? That if you have right, 2 points, and by the way, it says nothing where these points come from, right? It just says, okay, points assumed somehow given. Yeah, okay, I put it here, point and point, and then right, and then you can draw a straight line. Right. No, we may also denote this point A and B, for example, right? That's usual, and in Euclid we find that sort of notation. That's what first postulate does, right? It just says that given 2 points, produce a straight line or segment of straight line, because sometimes today in geometry, when people say straight line, they mean kind of infinite straight line, unbounded. But here Euclid always thinks about bounded lines, except, by the way, this postulate 2, which says produce a finite straight line continuously in a straight line. Now, what he means that we may actually continue our sorry. Yeah, so if now we are given already the segment, say AB, and then what we can do, we may continue it, you know, basically unlimitedly. He doesn't say here, he says continuously something, right? So, but we should expect that it's unlimited, so we may continue straight line that way. That's his second postulate. And what the third postulate says is this, that again we are given a straight line like AB, and we can make a circle with this center, say A, and radius AB. Okay, I think I don't have anything. Yeah, probably I'll not try to use this. and rather make just part of circle in that way, right? Yeah. And so these postulates 1, 2, 3, they give these rules for what is in English is called straight edge or Euler straight edge. Знаете такое слово? Или Euler and compass. Yeah. So basically it says that we can use ruler, как линейку, and compass, циркуль. Okay, the postulates 4 and 5 are also important, and particularly postulate 5, which actually gave rise to non-Euclidean geometry in the 19th century. But let me now just concentrate on this postulates 1, 3. So what we are talking is this construction by ruler and compass, циркулем и линейкой. And the important thing to notice is this, that actually postulates are not prepositions. Now try to recall some logic, right? Because remember, in logic, we talked about prepositions. When we derived, we talked about prepositions when we talked about propositional logic, and then we came to first order logic. Okay, there are some new entities, so to speak, that appeared like individuals, right? But still prepositions remain central. So logic was about how to, and particularly proof theory was how to derive new prepositions from some given prepositions. Remember, right? So we were given, I don't know, preposition A just as an example, and then we could introduce by introduction of conjunction, we introduce A and B. So it was a conjunction introduction, for example, right? And all our inferences were actually moves from prepositions to prepositions, or there is subtlety here, of course, because you may also talk about, say, assertions or judgments, and saying that it's not just preposition by asserted preposition. So preposition held as being true, right? But that's already a matter of interpretation. So I'm not really focusing on it again. So anyway, preposition remains central, while here, actually, kind of natural interpretation of this rule of postulate, say postulate 1, right? If we try interpret it, say logically, what is logical form of this? It's not actually, no, first of all, it's not a single preposition, and second thing, it's not really a rule for inferring one preposition or judgments from, say, sets of some other prepositions of judgments. And that's because, so what it does, basically, it says this, it says that we are given point A, right? And just saying that A is a point, I will use this syntax, which is actually comes from type theory. But let me just write this, right? That A is a point, so A belongs to types of points. Then that will be my first assumption. Then my second assumption B also a point. Okay, that's second assumption. And then I would have, by the way, something that Euclid assumes, but tacitly. So he does say this, but actually it's important, and that's important that these points are different, right? That A is not the same as B, otherwise it wouldn't work, or at least wouldn't work in the same way, right? And now, okay, I have this line, and line again would stand for, say, some sort of, syntactically speaking, it stands for derivation, right? But semantically speaking, let's see what it semantically stands for. So after all, I obtain a straight segment, right? Segment of straight line, which I may write as usual AB, right? But AB, this is a line, right? This is a different thing. It's not a point. It's a line, right? Now, the remark is this, that actually points, so basically it takes 2 points. It's kind of operation again, or, procedure, which takes in 2 different points. No, this is essentially they're different. We may say there is some proposition here, right? Because that A does not equal B, this is a proposition, right? Okay, and it outputs a line. So again, a kind of object which is not neither a point nor a proposition. So we have some new type of things here. And the important thing that we have here a rule, okay, but which applies not only to propositions, put it that way, right? It also applies to different types of things. It also applies to points, and what it outputs again is not just a proposition, it's a line. It's different thing, you see? So you have something that in a sense it's similar to inference rule in logic, but on the other hand, one wouldn't call this rule logical, right? Just drawing a line between 2 given points is not logic, it's geometry, right? It does not belong to logic, and still it has some kind of form which we may specify, just as we may specify a form of say logical inferences. Okay, yeah, that's important thing. Okay, I'm going to erase what I'm writing because clear, because otherwise I cannot. Good. Okay. Then, so postulates is the second set of principles called postulate. We didn't look all these postulates, but just first 3, it's enough. So I stop. Yeah. Then we have so-called common notions, also called axioms. So the word axiom actually comes as a different term for these common notions, and these again are rules. No, here it's actually, you may formalize this either saying it's implication or it's a rule. So, and there is not much difference because let me. So what does it say? Things equal to the same things are also equal. This is the first common notion or axiom. So if we try to symbolize it, you see Euclid does not symbolize, but we all learned to use symbols from 17th century much wider. So if these things so-called are A, B, C, then it, and if equal, we denote in the usual way. It says roughly this A equal to C, right, and B equal to C. So 2 things are equal to the same thing, C. Then okay, I can put conjunction here, right? And then implication sign. But actually, I prefer to write it in this Gensen style, so as a rule rather than as implication. So if I use this notation, that would be this, right? And then I conclude that A equals to B. And this, of course, that looks more like logical rule, right? Because we have this A equals C, B equals C, those are prepositions. Or if you assert them, they become judgments, right? Unlike point or whatever. A line, yeah. No, except you see, it's called common, and common stands here for the fact that it actually applies both for geometrical objects and to numbers, because this Euclid's element also includes three arithmetical books. Okay. No, again, we will not look now into arithmetical book, just for saying that those axioms are also like first axioms. Then okay, I also leave it to you look into other axioms. They they're also rules, or at least they're interpretable very natural as rules, such that they rule for certain prepositions, say, of certain form, right? No, remind, the idea of logic, general idea, is that it just works for any preposition, just whatever it's their subject matter. Here it's not for any preposition, right? Because it's, say, only for mathematical preposition. Moreover, for mathematical preposition of this particular form, that something is equal to something else, right? But nevertheless, and you see this fifth preposition is not actually about equality, is about being bigger than. But that's, you may look at that as a kind of negation of equality. No, at least it implies negation of equality. So it's closely related to equality, put it that way. No, again, actually, just for our purpose, yeah, let's only look for 2 and 3. Equal things are added to equal things, then the wholes are equal. So that's a bit more involved. It just says that what if I have A equal B, right? And I have C equal D, then I may conclude that A plus C equal things are added to equal things, that A plus C equals B plus D, right? And then, of course, you should somehow give semantic of this plus, and that's, again, that's certainly not a logical operation, plus, right? At least not in the usual sense, but it is a mathematical operation which Euclid actually defines for numbers in the usual way. So when these are numbers, it's the usual plus. With geometry is a bit more involved. What is the sum of two geometrical objects? But he has also a way to define it in rather natural way. So I'm not going into. Yeah, and the same with minus, with subtracted, right? So I can also write minus right here, and that would be separate rule, of course. Yeah. So that's how it works. So we have put it again, certain rules for just geometrical objects, for points and lines and circles. And second, we have rules for prepositions of specific form, as I just mentioned, or for equalities, if you like, right? So we have these two sets of rules. And now let us look into so-called proposition one. Yeah, what this book begins with just after, well, officially we may say it just begins with the definitions, continues with postulates and with these common notions. No, however, only after that we can come across anything like a proof. Okay, and so let's look just very simple first thing. Right, by the way, it's interesting, you see in Russian translation in English, it's these kind of units, they are called prepositions. So we have preposition one, while you see in Greek text we don't have this word preposition. This like alpha prime actually just stands for one. They used to have this kind of alphabetic numbering. By the way, in the old Russian texts, you find the same idea, how you may write numbers, and the idea is that just you take alphabet and your 10 letters, first 10 letters is just units, and next 10 letters are tens, and then you just combine them, you just put them together, right? Alpha, and you put prime just to show that it's not usual alpha, but alpha used as a number. Okay, yeah, but what I want to say now is, you see, there is no this word preposition, and actually I'll try to show you, and that's actually a reason why I coming back to Euclid today is to show that actually, technically speaking, it's not a preposition, right? It's not a preposition in this logical sense. You see what it reads: to construct an equilateral triangle on a given finite straight line. Okay, in other words, on a given segment. So remember, we even had these exercises, whether this, so you were giving a sentence, say in English, and asked, is it preposition or not, right? And if you say something like hello or have a nice day, those are not prepositions exactly, because kind of a test for testing a sentence, whether it is a preposition in a logical sense of the word or not, is to just to see whether or not it admits a truth value, right? If I say have a nice day, it's not something which is which can be true or false, right? It's you can call it a wish, a order, or whatever. However, it's not something that it can be true or false, right? And of course, there are many sentences in natural language that are also questions. If I say, what is the day today, or what is your name, whatever. Again, these those are grammatically sentences, but this kind of sentence simply does not do not admit truth values, right? In other words, cannot be true or false, all right? And so the same here, it's more mathematical context, but if we say to construct an equilateral triangle on a given straight line, it cannot be true or false, right? So you can understand it as a question, like how to construct, or you can understand it as a kind of demand, right? Как просьбу. No, by the way, there is also how say linguistic point, because ну, давайте вам тоже по-русски скажу. Вот в русском есть, и это такое специальное, на самом деле, свойство русского языка. Я не знаю, насколько оно, так сказать, распространено среди других языков. Это надо, вот, может быть, просить прокомментировать лингвистов. Но я точно знаю, что его вот нет ни в английском, ни в греческом, ни в древнегреческом. Это то, что у нас инфинитивы работают как повелительное наклонение. Да? Ну, когда можно сказать сидеть, стоять, лежать, вот в таком роде, это звучит как приказ, да? В английском такого нету, и в греческом такого нету. И здесь, если мы видим инфинитив глагола, да, то это не значит, что, ну, то есть мы какую-то вот эту модальность тут можем додумать, и, в принципе, это не так абсурдно, да, вот читать это как, ну, некоторое требование, что ли, вопрос, если угодно, но, в принципе, это, если тоже можно читать как просто такую совершенно абстрактную операцию, что ли, да, to construct a equilateral triangle given final line. So it just how say, it probably it's not even a sentence grammatically, right? That's again, you should ask people who are more, how say, in linguistics than myself, because you may say it's not a full sentence. What I mean, to construct an equilateral. So it sounds like a description, say, of a certain procedure, and that's basically what it is. But what I want to underline again, it does not admit truth values, right? It just so traditionally, in tradition, such things in Euclid, they are called problems. Okay, and that's important word that I want to. So it's a problem. По-русски, ну, у нас есть слово проблема, тоже калька с греческого, да, так же как, ну, или с латинского, из греческого, в данном случае латинская калька с греческого, слово это греческое. Ну, у нас есть еще русское слово, кстати, отдельное, кто знает, как можно слово проблема перевести на русский. Ну, синоним назвать.
Может быть, задача?
Да, я вот тоже об этом. Ну, конечно, у нас тоже есть там английские всякие слова, да, там task, например. Вот. Ну, в данном случае мы, так сказать, не особенно углубляемся в филологию, но важно. Но вот это слово проблема, problem или задача, они вот в данном случае, в данном контексте действительно такие традиционные. Yeah, and in Euclid, actually, problems are also actually the second also problem. This third one, oh, I think it's also problem. And so first so-called proposition, which is not a problem, it's actually number 4, and it's called a theorem. Again, we have it both in English and in Russian, just calc from Greek. So this is called a problem, and the problem is a proposition, right? Sorry, theorem is a proposition. So this is example of theorem, and because in the theorem we have a statement, right? We have a proposition. Now it's in precise logical says what it says. If two triangles have two corresponding sides equal and have the angles enclosed by the equal sides equal, you see it's rather messy, but it's actually what is so you have two triangles and you have BA equal, so you have basically this. So I can just mark it that way. So it's this AB is equal to ED, and BC is equal to EF. No, I think in this example, no, sorry, it's AC is equal to DF, like this, and angles are equals these angles, BAC and EDF. Right, then triangles are equal. You see, so this is already a theorem and proposition. So this is something to be proved, right? So what we talked earlier in our course about proof theory, right? That's a rather case of theorem, but it's remarkable and actually important that in a theory like, say, first book of Euclid's Elements, along with the theorems, you also have, say, things of different sort, which are called problems, and that's what I wanted actually to underline. And still, they are not quite separate. That's also interesting, right? That's actually what also makes this Euclid's Elements so special, that's historically is the first example of rather extended theory, right? No, as I told you, it contains 13 so-called books. No, books are like chapters. They are of different size, some are shorter, some are longer. But anyway, it's quite a lot of material, and it is deductively organized, which is amazing. And what I mean by deductively organized, or by deduction, that everything follows from what the earlier parts. So we start. No, at least this is an idea, right? Then you may probably criticize, say, here he used some assumption which was not really justified or even not made explicit, but at least it's clearly the idea that it's a big theory organized deductively, and deductively means that you have this list of say first principles like definitions, postulates, and common notions, or otherwise called axioms, and then everything follows. No, that's of course you should really look more precisely what does it mean to follow, and that's rather complicated. So it's not at all straightforward to we cannot say apply this natural deduction system that we studied and just show that how proposition 2 follows from axioms or proposition 1. Nevertheless, it's something like this, some sort of inference takes place. But let us just look a little bit how it works. Maybe it becomes clearer. So we have this problem of constructing equilateral or regular, otherwise called triangle, on given straight line, right? Now let's just, I hope all of you kind of understand how it works, right? No, I can tell you. So the idea, and then, so let's first look how it works, and then kind of try and analyze logical structure of the argument, right? So the idea is, of course, that you, so you have this segment AB given, so that's something you start from, right? So this AB is given as a part of your data, and that's, by the way, logically important, right? That's you see these propositions, they are not just some consequences of say axioms or postulate. They always involve certain condition, right? Something is given, and what is beforehand. In this particular preposition, I will use this word preposition just because there is no better word, even it's not preposition in logical sense as I just showed you. So what is given now, it's a segment, it's AB, yeah, and so to solve this problem is to construct this triangle such that is AB is one of its sides. So the solution is the construction and something else, actually, something more. But just wait, just let us see how it's constructed. No, of course, you use compass, circle. So you just use compass, you produce this circle, which here is denoted delta. Then you produce another circle with the same radius, AB, which here is called epsilon. Those letters are supposed to be Greek letters, I think, right? Epsilon. Then you find this intersection point gamma, right? And that, by the way, a point where this construction was criticized for many centuries, because indeed we don't find in Euclid's, in this list of postulates, any principle that tells us that two circles so constructed, they intersect, right? That such a point exists. That's something that is not, how to say, has no explicit justification in this proof, unless you may say it's kind of evident, right? You kind of think you simply see. So you specify this point gamma, and but only one thing, of course, important to say, when I say using compass, right? It's a kind of practical thing, right? That's how you do it on paper, or these Greek people, they actually used to do it on, on sand, or whatever it means. So this is an instrument, and but the task, of course, is mathematics, right? It's not a practical task, even if it's kind of related. So what you should say, logically or mathematically, that here you use this postulate number 3, right? We've seen it, which allows you to produce circle given a straight segment and using one of its endpoints as a center. Okay, so basically, when I say I use compass, you should understand that I use first postulate, third postulate number 3. Okay, and then we specify this point gamma. No, as I say, this is kind of allegedly a gap in all this reasoning, because but anyway, and then we use postulate number 1, remember, right, which allows us to draw a line from A or alpha to gamma, and another line from beta to gamma. That's the construction. Yeah, but question is it all? So I did all this construction and I somehow presented it formally. You may see that in Euclid, he just he describes all this in words, and this is of course very, how say, rather, on the one hand it's perfectly understandable, but on the other hand it's kind of messy, right? It's not very easy to read, neither in Greek or in English, or so it's not a question of language, but the just question is that some symbolic notation is really helpful in such situation, and if we don't have symbolic notation and we just use our normal phonetic writing, right, that's probably not the best tool to do that. But anyway, it's all perfectly readable. But important things is the following, that when this construction is, I don't know, probably there are some questions. Is it clear how construction is done? Or because it's pretty straightforward. It would be really cool if you have this compasses and ruler and can really do it. It's like in primary school or whatever. I think it's very, very useful exercise for all ages. I even have here a compass, I think. Yeah, I did not prepare it, but I should have it. Yes. Yeah, but I think it's clear. Or there are some questions. Please ask me if. Right, I think it's clear, right? You somehow you probably did this exercise. Did you? Or did you study this in school or not?
I think we did.
Yeah. Is there anyone in the room who didn't? Different question. No?
It seems to me that we did not.
Really?
Yes, but I'm not sure.
Yeah, you could just forget it or miss probably. Yeah, I see. Yeah, so it's a good opportunity to recapitulate. Okay, yeah. But now kind of more serious questions for you as already enlightened logicians. When we do this, right, so we accomplish this construction. And as I say, it's not just a practical construction, it's also theoretical in the sense that we actually refer to these postulates, right, as a principles, as a rules which are, how say, we are entitled to use in this kind of exercise, right? Is a rule of the game, if you like. But is it all? So can we say, okay, we did it, it's done. We did construct a equilateral triangle. If we just do that construction as I just described, or we need something more? What is your opinion? Well, okay, maybe the question is not really well posed, but what I want to straight that actually Euclid, and of course you should understand Euclid is not just kind of original mathematician, right? It's he's kind of collector. He collects, so that's he kind of just presented is kind of encyclopedia of Greek mathematical knowledge, right? It's not his original invention, right? So when I say Euclid, you should understand that it rather refers to kind of a standard, right, existing at his time and certainly applied much later through centuries, because as I told you, it just served, and even today serves at a certain degree, right, as a kind of example of how mathematical theory may look like. So what he does next is actually a proof, right? And that's interesting. Even if I said that's a problem is not a theorem, right? You may say there is nothing to prove. You should just do something, right? And by the way, you see that's also a way to distinguish between problem and theorem in Euclid. You just look at the very end where they have kind of special ending, and special ending for problem is this. This the meaning the above. Not even, you see they put it in brackets. That means that it doesn't exist in Greek original. The very thing it was required to do, right? And that important to do. So you did what was required, right? Or asked. And in case of theorem, you have you have, which is the very thing it was required to show. Ну, кстати, как это по-русски переводят, кто-нибудь знает? Тоже таким традиционным способом. Ну, есть такая формула, не знаю, кто-нибудь, может, слышал. Обычно это переводят так, что и требовалось доказать. Кто-нибудь слышал такое? Нет?
Yes. Yeah.
Well, доказать. Иногда это вот так переводят ЧТД, ну, сокращает. Иногда, кстати, это вот Андрей Николаевич Колмогоров, о котором, может, я сегодня скажу, такой придумал для этого специальный символ, который, ну, не то, что он совсем такой общепринятый, но используется такой вот просто черный квадратик, означает конец доказательства. А это идет, кстати, из латинского перевода, но на самом деле не совсем точного, который пишется так. Quod erat demonstrandum. И почему я говорю, что этот перевод не очень точный, поскольку вот у Евклида, видите, здесь разные слова. Вот как раз этот Фицпатрик, он корректно переводит, он не пишет доказать, он пишет как бы показать, to show. И это точнее, потому что слово доказательство вот у Евклида, оно имеет более узкий смысл, о котором я сейчас как раз хожу, а то, что означает конец, то есть у него как бы есть доказательство и показательство, или как, ну, если латинизмами говорить, то демонстрация и монстрация. Такой вот, кстати, какой-то новосибирский художник придумал такие монстрации, может быть, вы слышали. Ну и также по-гречески аподейкнуми и дейкнуми. И это важно, вот сейчас я скажу, почему. Так, давайте я уберу. Okay, we go back to problem. Yeah, so the thing is that, okay, you may reason as follows. Since it is a problem and you're supposed to do something, right, rather than to prove something, because proof refers to, say, preposition. You should show that something is true. That is a matter of proving. And here, apparently, you have nothing to prove, right? You should rather solve the problem. And this is a solution, as I just described, by using these postulates. So why you may need to prove something. And actually you do, or at least Euclid thinks, and after him, as I say, that the whole mathematical community, his contemporary, but also later, and even, let me say, today's community, why not? And this is because of the following. So you describe a procedure, okay? So you produced something, right? No, something that actually looks like triangle. However, you see what was the problem? To construct equilateral triangle. And now, how do you know that what you really constructed by using this postulate is an equilateral triangle on a given straight line, right? So you may call it verification, probably, right? So you see, it's very interesting and subtle. So on the one hand, there's a problem. It's something like, you know, you are looking for, like you're making a computation, right? Like you're adding numbers. You are not, how say, you are making no claims about numbers, right? You just take, say, number 2, number 3, you add them up and you have number 5. And here you have just one line, and then you apply these postulates, which allow you to construct more things, and finally you construct more things. However, you should construct, this is a difference between this simple arithmetical example and actually problem in that sense, right? Because problem just ask you to perform to obtain some specific thing, equilateral triangle on a given finite straight line. And if you simply describe the procedure, or your procedure itself should somehow, how to say, convince you that actually what you construct, it's exactly what you're supposed to construct or what you're asked to construct, right? Or as in Euclid's case, right? It does work like this. In that sense, these postulates are kind of silent. They are, you know, geometrical operations. They don't tell us anything. However, he provides a proof, you know, a proof of what? Of the fact that what you constructed, this ACB, is indeed an equilateral triangle. Well, he doesn't prove that it's triangle, takes this for granted. He does prove that it's on a given finite straight line. We may say it's clear by construction. However, he provides an argument that it is equilateral, right? And for that reason, he actually uses this first axiom, remember, right? This one, things equal to the same things are equal to one another. And also implicitly refers actually to definition of circle. Because remember, it's a part of definition of circle that its radii are equal, like AC equal to AB, right? So what happens here? By construction, we have that AC equal to AB, right? Because there are two radii of the same circle. This is one assumption. Okay, we can let me write it. Yeah, so we have by construction, we have that AC equal to AB. Okay, this is, we may say, by construction, because this is triangle, this is a circle, you know, postulate 1 refers to the circle, and this is a part of definition of the circle that radii are equal. Okay, this is one thing. Then by another construction, it's of the same type, but it's different. You may say that BC equal to IB, right? BC equal to AB. Similarly, right? And then what? Then you have actually instance of this first axiom. So we may conclude what? What we may conclude by first axiom. So this is a common notion 1. So what we can conclude? Two things equal to the same thing, right? AC equal to AB and BC equal to AB. So we conclude that AC equal to BC by this first axiom. Right, and now we see that all sides of triangle are equal to each other, right? AB equal to AC equal to CB. Exactly. No, we're assuming commutativity or equality, of course. Okay. So what we get, let's look once again how all this reasoning is structured. So we have this first part. It's called a proposition also. yeah, it's a bit how say ambiguous. And now I give you analysis, which is pretty much straightforward. We find it in a commentary to Euclid, written, I probably told you, by Neoplatonic called Proclus, much later, 800 years after Euclid was active. So it's 5th century already after the death of Christ. So it's new era. Okay, it's much later. Yeah, but anyway, it's just a historical source. So it seems that actually Euclid indeed has this kind of structure in his mind. Okay, so that's proposition. Then comes very important step here. This is a second. You see, it's analysis easy. It's almost not always, but very often just sentence by sentence. Let A be the given finest right line, right? So what happens? It's here. You see, you have just general description, say, of the problem, right? But then you specify what is given, and you give it a name, like a proper name. And I think at that point, people would make a picture. No, at least picture is kind of it's kind of supposed to be dynamic, right? You wouldn't draw everything just at one instance, right? You would rather at that point simply draw this, right? So okay, let's say I have this straight line given AB, okay, and this is called exposition. Well, again, it's just a English version of Latin names. I do not give you Greek names, of course. It's in Greek is ectasis. It's Proclus, of course, wrote in Greek, but later was all translated into Latin, and we still use it Latin as a part of English exposition. Oh, by the way, if you think about what we had already in our course as logical operations, remember rule of instantiation, right? So was say universal. No, it's analogy in that case, right? It's not, because this is not proposition, but it works somehow similarly. Remember, for example, existential instantiation, when we may conclude from say there exists such x, that p of x, right, with property x, and we may conclude from here p of say a, where a is a proper name of individual that has this property p. So that's something similar here, right? We start with just talk about kind of unspecified equilateral triangle or unspecified finite straight line, but finally we kind of draw this, we individuate, if you like, this straight line, right? We denote it AB, and we give it a name and picture it. Actually, yeah, it's of course also very important part of this enterprise is a drawing diagram. Otherwise, it simply wouldn't work. Okay, so that's next part. Oh, I cannot. I should clear it because, yeah. And then after this exposition comes another part. Yeah, so this is the exposition here. which is called usually determination. Well, it does say a lot, but basically it's what it does. Exposition was instantiation what was given, right? So this given finite straight line, we picked up one and call it AB and actually constructed it and made a picture of it, right? Let's call it AB. And then we kind of reformulated the problem in terms of this instantiated data. You see, and by the way, this modality like required is first appears at that point. It appears here. So it's required to construct equilateral triangle on the straight line and AB. So it kind of repeats or reproduces the problem, but not any longer as general problem, right? But kind of concrete problem. It's just how to do with this particular instance, AB, okay? Then follows all these things. Okay, I will not, that we just did. So construction, you make, you use postulate 3 or compass, if you like, right? Twice for point A as a center, point B as a center. Then you use postulate 1 for joining this A and B with this intersection point C. Okay, and this is called very naturally construction, right? This is a construction. Okay, and what follows, you see that this is not the end of the story. So what follows is this proof, and proof that what we constructed is indeed equilateral triangle, as I just told you. Okay, you can read it, blah, 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 blah. So it just says that the 3 sides of a constructed triangle, CA, AB, and BC, equal to one another. And this is a called demonstration, or probably proof. Let's call me proof. But you see, it's proof, it's kind of a more narrow sense. Probably I put this inverted commas to say this is a, because today we would say this whole thing is a proof, probably, right? And this is a more specific, right? And finally we have conclusion. Conclusion, and conclusion is it's kind of restates the thing, right? So we conclusion just how to say, it presents the solution in case of problem, right? So we say this triangle ABC is equilateral. We constructed it, right? So we know what it is, this ABC in terms of how to say, construction, and we did it according to rules. It didn't just pop out of the blue, right? It just was constructed by ruler and compass very seriously. Yeah, and we proved that it is indeed equilateral. So these conditions are satisfied, the problem is solved, and that we state in conclusion. And of course, kind of justification for this conclusion is this whole thing. You see, it's not just proof and not just construction, but this whole thing, which starts with this instantiation, which, okay, determination, no, we may say this both exposition and determination, it's kind of instantiation of the problem. We may put it that way, just two parts of what is given and what is required to do. Then we have construction again in this technical sense, and then we have this proof, you see, and proof does not refer already in this technical sense. It's this proof looks already very much like proofs we analyze, say, in natural deduction and things, right? Because it works just with propositions. This equals to that. It follows that this equals to that. And so we proved this proposition that ABC is equilateral triangle. And then we put all these things together, and we have the problem solved. And that's what we state conclusion, you see. And that's interesting that you see Euclid has this kind of double, I don't know, not double thinking, but double procedure, because he certainly does have this kind of geometrical, purely geometrical procedure, right, of constructing things, but by itself, it does not bring you solution, right? Because for solution, you need to complement this with this so-called, so to speak, propositional parts, because you need also to prove certain statement. And the statement is that what you constructed is indeed equilateral triangle rather than something else, right? And voila. So it works kind of on double level. There is a level of construction, geometrical construction, which is based on postulates, and the level of say just propositional inference. Yeah, and they work together. They work together to obtain the desired conclusion. Okay. Yes, please, if you have any questions. So next I'm going to show you example of a theorem, and probably I'll use not this theorem that I just showed you, but a bit a further theorem. A further theorem that tells us that about isosceles triangle, равнобедренный треугольник. The angles at the base are equal to one another. I think you know well this theorem again to school. But again, I will be interested now rather in a kind of structure of the argument. And actually, we are going to see that even this time it's a genuine theorem. It's not a problem. The structure of this reasoning is very much the same. And this is interesting and even puzzling in a sense. Okay, I just want to do this after the break probably, because but please, if you have any question about what I've just said about this problem of Euclid. Okay. Would any one of you just reproduce it, say, on the exam? If I ask you, solve this problem, construct, how you think? No, I'm kidding. Of course, it's all rather straightforward, rather simple, but okay, I think it's still very interesting from logical point of view, and probably not even fully understood. At least this is my opinion. Probably some logician would judge it differently, but I'm pretty sure we still don't understand how it works, of course. Ну, если пока нет вопросов, давайте прервемся на 20 минут, как у нас по расписанию. Окей?
Окей.
Угу. Ну, давайте продолжим. Меня слышно?
Yes.
Okay. Okay, so now let's look at the example of theorem. So that's so-called proposition 1 of first book was example of problem. And now we have example of theorem. Well, I already showed you one was actually the previous proposition 4, but I propose 5, look into 5 because it's more typical. This 4 is a bit special. So here in the very end, yes, we have this ending of this is the very thing was required to show, not to demonstrate, if you like. So here we have a statement, a general statement. So it is a proposition in the full logical sense. So for isosceles triangles, the angles at the base are equal to one another. You see, it has a like second part that if the equal sides are produced, so continued, then the angles under the base will be equal. But okay, let's just look into this first part. It's sufficient for our purposes. I think you're also familiar with this theorem. Углы при основании равнобедренных треугольников равны. But probably you are not so familiar with Euclid's proof, because I don't think that it's a school textbook. This proof is used. I've never seen at least. So let me again do as we did with this problem number 1. First, just I explained the mathematical part informally, so to speak, right? So you up to the point you don't have really difficulty, you understand this, and then we make like second round and see more precisely analyze the argument. So we need first the content and then formal analysis. So the idea is this, that we do something called construction or auxiliary construction. По-русски говорят, дополнительное построение. And this is rather remarkable, right? Because, of course, to find construction in a problem, it's, you may say, expected, because after all this problem is about construction, right? How to construct, say, regular triangle. And here you have a statement. You just need to prove something about what is given, and what is given is actually isosceles triangle. So triangles, two sides of which are equal to one another. So you prove certain fact, certain property of such triangles. So a priori, you might think, why I don't need any construction. But in fact, and this is, of course, a very important feature of this traditional geometry, that you do need that really to prove it, you need to, or at least prove it in that way that Euclid offers, you need to go beyond, so to speak, this triangle, right? You need, again, apply your postulates and probably use certain problems that were solved earlier to provide more construction, more kind of made your construction your complex, if you want, right? And that actually gives you the desired proof of this fact. That's very significant. Okay, we'll come back to this point later. So what we do, or what Euclid does as this auxiliary construction, is this. No, basically he continues sides of this triangle. Yeah, so and that's, by the way, again, that means that he uses which postulate, by the way, do you remember? So we studied 3 postulates. Which postulate is needed to continue this AB to, say, AD? Can't remember. It was actually postulate number 2. Remember that when it's segment is given, you may continue it indefinitely. Right, so you do this. First, you continue both these sides, okay? Then you actually make a new segment AF bigger than AB arbitrarily. So this kind of position of this point F is not uniquely determined. No, the same is true about D and A. It's just kind of indefinite points. But these points are definite in the sense you should really fix this F somehow beyond your B, but arbitrarily. So there is no precise rule. You can put this F a little bit further down or further up. That's also an important feature, that these procedures, you see, they include this arbitrary element. So they are not, in a sense, not precisely algorithmic in that sense. They assume kind of free choice. That respects, of course, certain conditions, because this F should be, say, AF should be bigger than AB. Otherwise, this construction doesn't work. So you fix this AF, right? And then you make the same on the other side. So you produce AG equal to AF, and that's, by the way, constitutes a new problem, right? How you can construct a segment equal to some given segment. But that is just also solved earlier in one of these, I think it's proposition 3, right? Or even proposition 2, I think. Right. To place straight line equal to a given straight line at a given point, right? So you cannot do it straightforwardly from the postulate 3, right? Because you need kind of transport the distance, and that's what this problem 2 allows to do. But I will not go to details. One who is interested may look. It's rather interesting construction, which I think again is very rarely used in modern textbooks. No, but anyway, it's rather plausible that it's doable by Euler and Compass, and actually it is doable. So you construct this point J such that AG is equal to AF, okay? And now, yeah, and then you also produce by postulate 1 FC and GB. So you have this, you see more triangles, new triangles that appear there. There is this intersection point here, but it's not needed in this proof. So it's not given even a name here. Yeah, and then you observe that actually what you consider these triangles, let me probably annotate. I can use another. Yeah. So what? Just consider these triangles. Okay, I just write it down here. AFC. Right, and so it's triangle AFC and sorry. And triangle kind of symmetric, right? AGB. AGB. So what you observe, they have this angle in common, right? Then you have AB equal AC, because triangle is isosceles is something what is given, right? And you also have AF by construction, AF equal AG, right? And this angle is shared, is common. So you have, you see, and now you use the theorem that tells you that you have two triangles such that they have common two triangles such that corresponding sides are equal, right? And angles are equal. And then the theorem says that triangles are equal, or we may say that actually the remaining parts are equal. Okay, I will not write all this down, but this is what we need, that all other corresponding angles and these sides about which we did know that they're equal, but according to this theorem 4, they are equal. And that's also important, right? That to prove a theorem, we use some earlier proved theorems. That's, of course, is very also fundamental and systematic feature. Now, that feature, by the way, it's kind of well modeled by, say, natural deduction, right? When we derive some proposition and then some further proposition. So if you think about this proposition as theorems, then you may say, okay, we first derive this property and then added some new assumptions about this isosceles triangle and derive some new theorems using this earlier proved theorem. But of course, we should also check that these conditions of this theorem, right, assumptions are satisfied here. And that's what I'm doing here, right? That corresponding sides are equal. And no, I put it that, say, this angle A is shared, is shared, okay? Yeah, so what you conclude using this proposition 4, that actually that these triangles are equal, okay? These triangles are equal, and particularly I'm interested in the fact that this AFC, this straight line, is equal to what? To GB, right? Because triangles are equal. And at that point, we consider two further triangles, and namely triangle FBC and triangle FBC and GCB. Okay. And so what? We prove that BF equal CJ. By the way, here Euclid, because first we constructed AF equal AG, right? But since AB is equal AC, because triangle isosceles, these remaining parts are also equal by third axiom, right? If we subtract equals from equals, the remains are also equal. So that's why if BF is equal to GC, right? Then, yeah, these angles G and F are also equal, right? As the corresponding parts of what we proved earlier. Angle F is equal to angle G, right? And what else? And yeah, and we just proved already that FC is equal to GC. Right, it's here. So we conclude that these triangles are also equal. FBC equal triangle GCB, right? Right. So these are smaller triangles. I can put them that way. Are also equal, but that means what? That again, corresponding angles are equal. So we have these big angles. Okay. Yeah, that was a bad idea to put. Okay. So these angles are equal, right? Again, as corresponding angles of these big triangles. I would call them big and small. Okay. And now these small angles are also equal as corresponding angle of small triangles. And that means that we may subtract small angles from big angles. And after all, we, that way, we conclude that angles, no, let me now say them ABC, angle ABC equal as a remaining part to ACB. Yeah, you see, yeah, and that concludes the proof. So we proved that angles at the base are diagonal, but you see now it's involved again a bit of reasoning. I don't know, it's clear for everyone or not. Yeah. No, of course, I just reproduce this proof in a rather messy way, but now we may look more formally. And I think it's a standard procedure, right? You prove some theorem in kind of informal way, just have an idea how it goes, and then you write it down, say, more rigorously and see whether there are some caveats. Probably there were mistakes, or even not mistakes. You justify better each step, and that's practically speaking just the way how mathematics works, even research mathematics. Okay. No, okay, I really recommend you to how say to follow, because each step is very elementary, but when there is a certain number of such steps, that's already makes some, say, intellectual, no, if not really a challenge, but some difficulty, right? Because you should really put these things together and follow construction, and that of course is very very short construction, and in real mathematics there are much longer much longer reasoning and much more complicated constructions, not speaking that much more abstract and so on. Okay. So ask if you want me question, or otherwise I just clear all this. And now I want to look kind of globally again, right? What's going on here? And actually, as you can see, the same structure that we specified in case of problem, it's actually preserved in case of theorem, just the same. So we start with a kind of general proposition, and now it's a proposition in logical sense. It's admits truth value, right? It could be true or false. No, it's, of course, it should be read as universal, right? There is nothing, it just says for isolysis just a plural, but it should be assumed that he tacitly uses universal quantifier, so to speak, right? So that's that is supposed to work for all isosceles triangles, right? For all So it has this form for all x such that say is and this is a predicate just that said that my x is isosceles triangles, and that implies that you see it's not straightforward actually to formalize no say a of x where a of x simply means reads angles at the base are equal, but it's of course it's very how say imprecise formalization, and if you want to make it more precise, it's not straightforward. At the base are equal, but this general structure is like this, equal, right? So what I want to emphasize now is this universal quantifier once again. Okay. So we have this universal statement. Then we do what we called exposition. So we say let ABC isosceles triangle, right? So let's pick up some particular triangle. And that's, by the way, that time is very precisely what is called in logic universal instantiation, right? Because we instantiate our general claim about triangle with a certain triangle ABC, no? And once again, now we say that the angle ABC is equal ACB. So again, this statement is specified, right, in individual case, so to speak. So it's indeed universal instantiation. But now what follows, as I already told you a minute ago, it's kind of interesting from logical point of view and not quite expected, if you like, right? Actually, philosopher Immanuel Kant, he made his whole understanding of mathematics more or less on that basis. So we need a construction, as I thought, right? So instead of just looking what follows from what, we are making kind of additional construction, which I just described. I will not describe you again, right? And the reason is that that construction really helps us, allows us to produce the required argument, the required proof. Yes, and so again, this is longer, you see. Okay, so I just already explained it informally, so we'll not follow all of it word by word, but that's finally we come to that conclusion that these angles ABC, GCB, so these two angles at the base of the given triangle, they turn out to be equal, and we prove it using this additional construction, these additional triangles, and using earlier proof theorem about triangles, you see. So somehow this additional construction empowers us to provide this inference, if you like, this proof. Well, if you think about in terms of say natural deduction, you may think about this additional construction as a kind of hypothesis, additional assumption, which is basically discharged, right? Because we don't use it actually finally in the sense of additional assumption, right? So we don't really add it to our argument, right? We rather We rather produce it as something that is, say, doable in this framework, right? And that's of course true. That's our postulates. They so put it that way, these additional assumptions, they kind of reduce to these postulates, and postulates are assumptions kind of for all these problems and theories. Yes, but of course the problem is that as I told you, construction is not a logical procedure, right, by itself. Unlike, say, instantiation, that's something logical. We say, okay, first we talk about, say something about all triangles, but then say, okay, let's pick up some arbitrary triangle and work with that. That looks like logical operation, and of course construction does not look like logical operation. No, anyway, it's interesting that we have just the same structure, right? So we have this kind of instantiation, universal instantiation. Yeah, and by the way, in the end, we come to generalization. So basically, we prove this just for particular construction, particular triangle ABC, but then we claim it works for all triangles, and that's because it's universal generalization, because we don't use any specific property of this ABC, except that it is isosceles, and that which was given in a condition in our theory. Okay, so that we can do, but we cannot use any other property, and actually we didn't. Okay. Yes. So so you see, there is the same structure as in the case of a problem, except then we might say that proof had kind of auxiliary role. Понимаете, auxiliary как вспомогательное. Right? So in the center was the construction, but we also use the proof in order to show that what we constructed, it's actually what we were asked to construct, right? So we may say proof is used here as a verification of our construction, right? While in the case of theorem, it's the other way around. We may say the center is a proof, right? A proof that concludes with our theorem, right? So we come to this conclusion, and that's what is proof supposed to be. However, as a part of the argument, we also use construction, addition construction, which was made according to the same rule as construction in problems. And more generally, you see, when we talk about this deductive order in Euclid's elements, it's actually this mixture. There are problems and theorems, and problems are used in this so-called additional construction in proofs of theorems, and the other way around. The theorems are used in proofs which makes part of problems. So there is this sort of duality between problems and theorems. Right. No, okay, I think I may. Okay, let's probably we have some questions, just more general questions about this geometry or whatever. Yeah, of course, from, say, modern point of view, it might look a little bit strange, this geometry. For example, one may ask, why ruler and compass, right? Why not using some other, why these rules of the game? And I think there are some specific answer which related to the fact that indeed for, say, these mathematicians, like straight line and circle were some sort of distinguished objects. Yeah, but But it's very, very interesting and important, of course, theory in terms of. By the way, do you know that not all problems are solvable? Yeah, let's talk about this. That's also very important general point about, say, Euclid's geometry. Yeah, let us talk about this a little bit. Oh, yeah. Unsolvable problems. Yeah, and I unsolvable, I really put in inverted comma because I will argue that it's kind of ambiguous and probably wrong to call them unsolvable, but I will start with that because I think unsolvable problems. Yeah. No, so kind of moral of what I've said today is that problems, in fact, are as much important in mathematics as, say, theorems. And that's pretty much concerns today's mathematics. I will not try to justify this claim, say, referring to some modern mathematics, but I think you intuitively it's quite plausible, right? Particularly if we are thinking about, say, applied mathematics. We say want to compute something, right? We have certain data and we want to compute. We want, for example, predict the dynamic, say, of say climate change, right? Suppose you have some mathematical model of climate, and there are such things. That's special industry, of course, and you want to make some plausible prediction what will happen with climate, say under certain conditions, say if pollution doesn't stop or if it does stop or whatever, right? So you want to use your model somehow to make certain prediction, and that of course constitutes a mathematical problem. All right, no, to say fairly, it's also kind of computer problem, right? Because these mathematical models are not, they're rather computer models. They are kind of not just pieces of pure mathematics. But anyway, that's clearly a problem, right? It's not a theory. Yeah, of course, if you make certain prediction, you can formulate the result in say in propositional form, right? Say I predict that, say, in 100 years average temperature will be such and such. So it's all allows to describe, but what you actually want to do with your model is somehow construct say certain situation in it, right? It's what you do. And I think you may think about many other examples. So this problem in mathematics is not at all outdated concept, right? Of course, certain problems have this form, prove this theorem, right? So we may also call this problem. So if you have a mathematical conjecture, and there are many around, for example, there is this twin primes conjecture, right? That prime numbers which just are the form like 11, 13, or say 17, 19, such that the difference is just 2, right? They are kind of close. So it's a conjecture that number of such pairs is infinite. However, it's open. Nobody neither proved it nor disproved it. Yeah, so there are many. Until recently, Fermat's last theorem was such a conjecture, but now it's proved, like couple of decades ago. So, but there is of course lot of open questions. So these things we may also call problems, right? However, there are also more general problems. If I say, please construct equilateral triangle, it's not that I'm asking you to prove something, right? I rather ask you to produce a certain mathematical object with certain properties according to certain rules, right? So that's different kinds. So problems generally, it's more general. Sorry for being redundant. Than just proving a theory, okay? But then we should really talk more a little bit. What is actually solution of the problem? No, okay. In case of triangle, it was clear what was the solution, right? It was a kind of question requirement, and we gave an answer, and even verified this answer with the proof. However, let me just give you another couple of problems. Do you know, this is a question for you now, I will start with that, how to bisect an angle. So now it's given what is given is an angle, okay? And what I want to do is cut it in two equal parts. And again, I want to play by the same, according to the same rules. So what I have in mind is this ruler and compass construction. How to do this with ruler and compass. Does anyone know how to do this? No? Okay, maybe another. Then another problem. I simply give you a straight line. Okay. And now I simply want to cut it into equal halves. So I want to find such C, but I put quotation mark, meaning that I don't know where it is. Yes, such that AC equal to CB. Again, quotation mark. So I want to find such a C or construct it according to postulate, or in other words, by the ruler and compass. Actually, it's if you think about this problem about triangle that we've solved, probably you may find a solution also for that one.
I guess we need to draw like дуга, a half of a circle.
Yeah, no,
On each.
we may also draw the whole circle, right?
Yes, we may just draw two equal circles with two equal radius on the.
So I don't know.
On like both sides.
Yeah, so we do basically the same construction with triangle, but now we right, we are doing it on both sides. Right, then we just found that point and we stop, but now we actually continue, right, a little bit. So so let's call it M, for example, right? And that's, we find N, and then what?
So these 2 points of intersection, we need to draw a straight line between them.
My line is not very straight, but yes. Okay, yes. But you see, we also need to prove it. How you would prove it, actually? Yeah. So that seems to be correct, right? No, okay, let's not spend time for this, but I just want you somehow realize and feel that it's not enough just to describe the procedure, but you also need to give a proof why it gives you what you say it does, right? So you need some proof. I don't know, you might look for some triangles, basically. It's the usual technique of Euclid, but some, again, proof is given. Okay, but so far it's fine. It's but with angle, you don't know. No, actually, it's kind of similar construction. You're first making AB equal to, say, let me just put this C here, right? So I'm making AB equal to AC. And then I may, what, yeah, and then I'm making, actually by any radius, but I may use the same radius. I make a circle with the center in C, and then another circle in center B, and here I have intersection point, right? And then I draw my line here. Okay. And again, of course, okay, one needs a proof, which I skip. Okay, but what about actually dividing segment into 3 parts? No. Or actually to any other number of parts. Who knows how to do this? Not 2 parts, but say 3 parts. Mm-hmm. Yeah. Okay, let me show you. It's also doable. So what I need, it's to construct an angle, okay? Arbitrary angle, again, arbitrarily and logically with arbitrarily is interesting. So this AB is given, right? And then I just constructing some equal, say 3 equal segments, again, of arbitrary length. Say C1, C2, C3. Okay, that second step, arbitrary length. Then next step, what I do, I produce C3 and B, so I'm making this triangle. Okay, and final step, I'm making parallel lines. Of course, I should learn also how to make parallel lines. That's a separate problem, but that's doable. And so I'm making parallel lines like this. Okay, and now it's called theorem of Thales, theorem of Alesa. That that actually what I get this D1 or D2. That actually, since these were equal by construction, these are also equal. Yeah, so it's also doable. Okay, but now next question, what is about trisecting a triangle? Did anybody hear anything about this? So we solved this bisection problem. No, of course, with some reservation, we did not really follow it, but yeah, that's usual thing that we need to refer to some details and then one who really wants to understand this just looks and follows everything. Otherwise, just she should believe me. Yeah, or look into the book. Okay, but what about trisecting? Yeah, so we bisected angle and bisected segment, straight segment. We trisected segment, and actually you can do the same for any number of parts. But now we want trisect an angle. So to produce a construction of that sort, right? Such that these are equal. Of course, we may, if I just start with some angle, right, I can kind of triple it, right? So if it's not too large, right, I can really repeat it like this and just make that kind of construction. But the problem is different. The problem is that I start with this bigger angle and won't divide it into 3 parts. Have you ever heard about this one? No? No, apparently not. So tell me the story, because this one actually is unlike the 3 others, and this is because it's turns out to be unsolvable. Yeah, but let's discuss what it means exactly, right? What it means more precisely. No, the story is that people, of course, very naturally, when they did this kind of geometry, they very naturally asked that question, and then they tried a lot of things, and it just didn't work. They didn't find anything. And of course, if you don't find anything, you can tell that it's impossible, right? However, it was much later, and somehow, thanks to discoveries that were made, say, in 17th century, where was established this closed link between, say, geometry and algebra. No, something like coordinate system, but actually much more. And using these methods, only in 19th century, it was rigorously proved that is unsolvable, meaning by ruler and compass. So you see, a priori, you have these rules of the game, right? You are allowed to construct only certain things. No, and otherwise, if you don't have rules of the game, you are nothing to play with, of course, right? Otherwise, you can do whatever, and it is no longer mathematics. It may be some other interesting activity, but not mathematics, right? So you see, you solve that problem, you solve this problem. Actually, or people, even in Euclid, you can find a lot of very sophisticated kind of long construction. It's rather much more difficult mathematical result. But this one really resisted, and actually there were 2 more that kind of famous which resisted. Another was to construct a square equal to a circle. No, equal, it's what we call today by air, по площади. Okay, so if I have this radius, say 1 whatever meter, then what is the area? It's called pi, right? It's a number, and so I should have the side of the square root of pi, right? So and no, they didn't think in these terms of square root or pi, but they just were thinking how to make this construction and prove. So given a circle, construct certain square and provide a proof that they're equal. Okay, and the third was about doubling a cube. You remember we considered, I think, in the beginning of this course, doubling a square, and that works. But what about doubling a cube, right? And that, again, in modern notation, if the side is 1, so you need a cubic square of 2. It should be side of this bigger cube. Okay, draw it. Yeah, and so again, somehow the problem resisted, and that's continued for centuries, you see, and only in no, I would say in 17th centuries people somehow develop a technique which I cannot really describe in this course, even if I think it's very interesting and actually accessible. It's can be presented in an elementary way. That really allowed to answer that kind of questions, whether something is possible or not, because a priori, right, why it should be possible at all, right? So it could be difficult or it could be just impossible for certain reasons, right? Nothing guarantees that it is possible. And that's exactly what was later proved. No, I can say in case of that was is a quadrature of circle, как квадратура круга по-русски называется, right? And here I can give you basic argument, and the argument is that if you coordinate, right, if you use coordinate plane and interpret your geometrical construction in terms of numbers, then you may observe that actually all these constructions, they basically perform usual arithmetical operations plus square root, right? And but number pi is so-called transcendental number, so it's not a fraction and it's not an algebraic number, so it's not a solution of some, say, equation with rational coefficients. So yeah, but by the way, this proof that this transcendental number also was obtained only in the 19th century. It's not easy at all. But if you combine these facts, you can see that just starting with a say, square, you can never obtain pi, or the other way around, if you starting with the circle, right, and radius 1, and here you need to obtain square root of pi. Okay, square root you can obtain with the compass, but pi you cannot obtain. So this construction is undoable. And this trisectional angle for different reasons is also undoable. As we know it today, and as I say, to prove it, really what was needed is a kind of really new kind of theory. So you cannot just prove it using this Euclid's theory. And by the way, that's kind of how to say, defect of this theory, that it may how say, it allows to formulate problems which are perfectly meaningful, right? This is a meaningful problem in Euclidean geometry, but that has no solution, and we cannot prove in this theory, just using this theory, that there is no solution. But okay, that's just a part of general mathematical culture. But now we are doing logic, right? So let's just concentrate only on logical part, so to speak, right? So let us, what it means that problem is unsolvable. Let us somehow fix terms, so to speak, right? Because when we actually proved that we cannot perform the desired construction, we solved the problem, right? So it is solved, and it has been solved. So we cannot say now trisection of angle, it's an open problem. No, it's no longer. We know the answer. And the answer is that this construction is undoable, is impossible by a ruler and compass. And so in that sense, we know the solution. The problem is solved. So it may be useful in that case to distinguish your positive solution, right? And call positive solution will be a solution that exhibits the required construction, right? As we did with triangle, but also negative solution. Negative solution. Right, which of course kind of tricky as a concept, negative solution, right? However, perfectly reasonable. So by negative solution, no, roughly speaking, it's just a proof that the problem does not have a positive solution, right? Which is a bit tricky, right? Because remember, I told you that to prove something is not the general case of the problem. So certain problems like this one are not about proving something, but now at least this case of negative solution looks like it's the case of proving something, right? Proving that there is no positive solution. Okay, let me clear this and say and put that way, just negative solution of a problem is a proof of say problem P, right? A proof that P has no positive solution. And what is positive solution I somehow assume is sufficiently transparent. Positive solution. Okay. Yeah, so we will not say that. So that's why saying that problem is unsolvable, it's kind of tricky, right? As I told you. So more precise statement would be it has no. So it could be different situation, right? Problem could be open. So indeed, nobody would know the answer. But that's just in case of certain, say, I wouldn't say theorem, but rather conjectures, right? As this twin primes conjecture, for example, which is open. It could be the case that problem is solved positively, but it could be also the case when this problem is solved negatively, and it's still solved. So it's kind of ambiguous to call, in that case, problem unsolvable. Okay. Yeah, I think it's probably interesting piece of logic which probably has some relevance even outside mathematics, right? So we may have problems even in real life which are, say, not solvable positively. Yeah. So yeah, probably some questions about positive and negative solutions. No, by the way, one thing which should not be actually one case of negative solution we already also came across again at the beginning of this course, because remember I asked you to find the common measure for a side of the square its diagonal, remember? And then we proved together, we provided that proof that this is impossible. So if I formulate this as a problem, and I think it's a very most natural way to formulate this, right? That's also example of negative solution. But there is interesting difference here with the case, say, of trisecting angle, because say trisected angle is not a contradictory construction. There is, if we simply assume that such a thing exists, right? Such a construction exists, no contradiction will follow. So this negative solution actually is related exactly to rules according to which we play, right? Basically to this postulate. So it's precisely, it's impossible to construct by Euler compass, but it is possible to construct by some other means, by the way, and other postulates, if you want, more powerful. While in that case, it's actually impossible construction, right? Remember, we actually, when we proved that it was impossible, we did not refer to any method of producing it, right? We simply made this reasoning ad absurdum, but not reductio ad absurdum, actually, right? Because we simply assumed that it's done, right? Somehow, and then we derived a contradiction. So it's different. You see, this is a really impossible construction. The diagonal of the square and its side kind of measured by the same measure, so to speak, right? While this trisected, there is nothing impossible in trisected angle. And what is impossible is to do this by ruler and compass. And that, of course, is a different thing. Okay. Okay. No, okay, maybe we have a little bit of time left, and probably I'll show you one thing just to conclude that discussion and probably prepare what I was going to tell you next week. So next week is what is 23rd of May. Okay. There is actually, did you ever heard the name of Andrei Nikolaevich Kolmogorov? Ну, давайте я вам эту часть по-русски расскажу, ладно? Раз уж мы говорим об Андрее Николаевиче Колмогорове. Кто-нибудь слышал это имя?
Unfortunately not.
Очень давно, да? Сейчас, одну секундочку. Ну, давайте сейчас откроем. Сейчас хотя бы Википедию. Ну, это математик поколения... Вот смотрите. Ну, то есть вот родился он в начале века. Ну, один из крупнейших, некоторые говорят, самый крупный. Ну, один из точно вот крупнейших математиков 20 века. Причем, так сказать, без скидки там на, так сказать, русское происхождение. То есть это не только для России, конечно, для всего мира. Вот, ну, вот в 1903 году умер он в 1987. Я как-то, к сожалению, не застал уже его в активном состоянии. Но, так сказать, я сейчас не буду пытаться его вклад в математику как-то описать в целом, потому что он, ну вот он был из таких математиков, которые, в общем-то, нельзя сказать, что он в чем-то специализировался. Он действительно в очень, так сказать, разные области математики, включая, кстати, прикладную математику. Вот тут даже написано философия, история, методология. Но в данном случае я именно хочу сказать о его вкладе в логику, который не такой уж большой. Ну, в общем, в том смысле, что он не так уж много ей занимался. Ну, по крайней мере, вот так непосредственно. Он занимался, кстати, вот один был из пионеров такой вычислительной сложности, то есть тогда еще даже таких современных компьютеров не было или еще только начинали появляться, но вот он очень много сделал в плане такой, ну, что ему, той математики, которая вот служит основанием для теории вычислений и компьютерной науки. Вот, но это, так сказать, я еще раз говорю, я сейчас не буду даже пытаться... Так, подождите, а не видно ничего, да? Что... Сейчас.
Не видно.
Угу. Ну вот я тут просто вот портрет. Да, тут очень много. Тут написано, ну вот он был в Московском университете, был заведующим кафедрой. В последнее время он был заведующим кафедрой логики, между прочим. То есть может быть, что это вот, хотя он этим очень много не занимался, но может быть, это как раз как бы отражает его такой вот интерес очень глубинный. Да, но я сейчас хочу показать вам только одну статью. Так, вот она. Видно так экран, нет? Сейчас или, наверное... Нет, вот. Вот, эту статью, она 1932 года, ее оригинал на немецком языке был. Но есть вот русский перевод, сделанный одним из учеников, тоже, к сожалению, уже скончавшимся Владимиром Андреевичем Успенским, и есть тоже английский перевод. Так, а где русский-то у меня? Ну, да, ну ладно, пускай будет английский. Ну, она так называется, а интерпретации... На самом деле она по-немецки называется немножко не так, скорее как бы о смысле, что ли, вот этой интуиционистской логики. Ну, что такое интуиционистская логика, я уже говорил, да, то есть это вот та самая логика без правила исключенного третьего. Ну, мы с вами познакомились с ней вот именно в таком варианте натурального вывода. Ну, ее же можно представить и в стиле Гильберта, так сказать, как. Ну, суть от этого совершенно не меняется. Вот, ну, значит, в чем интерес этой статьи? Потому что в этой статье он как раз придумал вот следующую вещь, чтобы создать, вот как бы наряду с теоретической логикой вообще, да, вот он говорит, with the development of theoretical logic, which systematizes the scheme of proofs. Ну, подождите, давайте я вам все-таки сейчас по-русски тоже открою. Она у меня... Так, сейчас, одну секунду. Proofs. А. Сейчас, ребята, извините, у меня куда-то это убежала русская. Сейчас я найду. Так, вот здесь она. Вот, вот. Вот. Ага. Видно? Вот. Значит, вот он говорит следующее. Наряду с теоретической логикой, систематизирующей схемы доказательств теоретических истин, возможна систематизация схем решений задач. Ну, то, что вот мы с вами говорили, проблема, да, вот он по-русски, ну, собственно, он-то немец, по-немецки, ну, говорит это уже вот переводчики. Ну, я думаю, что по-русски он тоже называл это задачей. Вот. Например, геометрических задач на построение. То есть вот то, что мы с вами как раз разбирали. Вот. Ну и вот это то, что он говорит, принцип силлогизма, это более-менее modus ponens, он имеет в виду. И вот, например, что это значит? Что если нам дан modus ponens, давайте я сейчас напишу. Все помнят, что такое modus ponens, да? Помните, как у нас это было устроено? Ну, давайте вот так я напишу. P и Q, да? P, дальше импликации с P, Q, и отсюда мы выводим Q. Да? Ну, это то, что в натуральном выводе называется удалением импликации. Да? P из P из Q и P и Q. Ну, то есть обычно мы об этих P и Q думаем как о каких-то утверждениях, так? Которые там истинны или ложны. Вот. Но как раз вот Андрей Николаевич Колмогоров предложил подумать о них как о задачах. Вот предположим, вы решили задачку P, да? Там построили, допустим, правильный треугольник. Так? Дальше, вот что такое задачка P импликация Q? Значит, идея такая, что здесь есть такое отношение сведения. То есть вы научились каким образом решать задачу Q с помощью задачи P. И вот свести решение задачи Q к решению задачи P – это как раз смысл, семантика вот этой импликации. Ну, новая семантика, вот, которую он предлагает. Да, не в терминах истинных значений, не в терминах пропозиции, а вот в терминах задачек. Да, то есть решить задачку P стрелочка Q значит научиться сводить решение задачки Q к задачке P. Ну вот если угодно, это, конечно, будет недостаточно. Я примерно показал, вот когда мы делили пополам, да, этот отрезок, я бы мог так более подробно сказать так, давайте вот тут построим сначала так треугольник, а потом еще один треугольник, да, и потом разделим. И вот у нас получится как раз. То есть мы здесь использовали решение, ну, мы еще кое-что использовали, ну, давайте этим, так сказать, пренебрежем, да, тогда вот если мы умеем строить треугольник, мы умеем решать задачку Q. Ну и, собственно, этот вывод означает, вот P, значит, мы, допустим, построили треугольник, Q, это мы делим отрезок пополам с помощью треугольника, так, ну и, соответственно, вот у нас вывод. Строим треугольник, учимся сводить деление пополам к построению треугольника, отсюда выводится, что мы умеем делить пополам отрезок. Вот в таком духе, да, то есть мы пользуемся тем же синтаксисом, но вместо того, чтобы думать об этих переменных как о высказываниях, мы думаем о них как о задачках. Вот. И ну, в общем, у этой истории есть, хотя вот дальше, собственно, сам Андрей Николаевич ничего такого не публиковал, особенно по логике, но на самом деле есть очень много, так сказать, всякого интересного продолжения, но при этом, по крайней мере, вот насколько я могу судить, полностью все, что он хотел тут, так сказать, задумал, до сих пор мы это в логике делать не умеем. То есть мы можем действительно какие-то символизмы использовать, ну, придумывать, да, специально для задачек, ну, или вот так же, как, собственно, он здесь делает, он использует уже готовый формализм для интуиционистской логики, меняя его интерпретацию. Вот. Но вот то, что остается открытым, в общем-то, вопросом в логике, это как нам понять, вот как задачки связаны как раз с высказыванием, понимаете? Там же у нас, ну вот даже в наших примерах было, да, когда мы, допустим, этот треугольник строили, то есть вот там было построение, а внутри этого построения еще у нас было такое доказательство, которое вот верифицирует. И как вот эти вещи работают вместе, в общем, не очень понятно. Вот вопрос, может быть, вы сами как бы догадаетесь, а что такое будет отрицание P, да? Ну, раз мы уж задумали, что мы хотим всю вот так переосмыслить все наши логические операции, ну, тогда вроде как отрицание же тоже логическая операция. Вот что такое не P? Ну, значит, P – это какая-то задачка, так? Причем, понимаете, задачку здесь, конечно, надо понимать вместе с ее решением. Вот это тоже важно. Да? Вот здесь, когда я даже говорил не просто задачка P, задачка Q сводится к задачке P. Ну, то есть можно так сказать, но что это значит? Это значит, что решение задачки Q сводится к решению задачки P. Да? Поэтому здесь вот надо как-то понять, ну, говорим ли мы просто о задачах или как бы о решенных задачах. Ну, скорее, наверное, все-таки о решенных, потому что это, ну, так же, как когда мы говорим о высказываниях, мы, ну, не всегда и в интуиционистской логике, но обычно мы предполагаем, что они вот истинные или ложные, даже если мы, допустим, не знаем истинно или ложные. Ну, по крайней мере, в классическом случае. Вот. Ну, так или иначе, нам нужно какой-то иметь вариант для того, чтобы какой-то смысл придать вот этому выражению не P. Ну, подсказка, смотрите, какая, что именно в интуиционистской-то логике вот это не P, это тоже такая штука, в общем, проблематичная, да, и мы не можем просто вот это отрицание, например, определить вот с помощью таблицы истинности, как мы это делали вот в классическом случае. Просто сказать, что у нас истина превращается в ложь и наоборот. Помните, мы с вами все возились там с этими двойными отрицаниями. Собственно, мы можем без правила исключенного третьего доказать, что из P следует, что не P. Вот. Но мы не можем доказать, что из не P следует P. Вот этого у нас в интуиционистской логике этого нет. И мы с вами это подробно достаточно разбирали, помните? Вот. Поэтому, конечно, что такое вообще отрицание в интуиционистской логике, это тоже немножко проблематично, но обычный ответ на это такой. Помните, что на самом деле мы просто по определению, что если у нас есть способ из P вывести противоречие, помните, вот так, да? И это у нас называлось правило введения отрицания. Но, собственно, вот это правило введения мы можем как раз использовать в данном случае как объяснение того, что это вообще такое отрицание, да? Значит, у нас не P имеет место, когда оно приводится к противоречию. Вот что такое не P. А вот что такое будет не P, если P у нас это теперь не высказывание, а проблема? Вот как вы думаете?
Может быть, что это будет задача как бы с вот этим negative solution?
Да, с отрицательным решением. Да, вот идея тоже именно в этом. Ну да, тем более, что если, видите, он же хотел весь этот синтаксис сохранить, то есть вот это же правило работает и в этом случае. Ну, единственное, что вот здесь вот это противоречие, надо тоже подумать, как его переосмыслить, так сказать, да. Потому что, конечно, в наших обычных примерах это, в общем-то, все равно обычно, ну вот это вот я говорю, как раз такая вещь, которая я, по крайней мере, не знаю о хороших реализациях. Я еще вот сейчас как раз статью на эту тему готовлю, еще со всеми, так сказать, главными логиками это не успел обговорить, но вот мое понимание в том, что все равно, когда вот эти доказательства, что решения нет, они именно идут, вот это именно доказательства, да, то есть именно доказательство утверждения, что решения нет. Но возможно вот действительно другой подход, чтобы вообще не ввязывать сюда утверждение, а как бы по аналогии с вот этим фалсумом какой-то придумать такой специальный объект. Вот один автор придумал его называть панацеей. Помните, вот как у нас из фалсума следует что угодно, да, то есть у нас вот есть просто такое правило, что любое А там следует из фалсума. Вот также в случае проблем, если у нас такая штука получилась, то из нее как бы решается любая проблема. Ну, что как раз показывает ее такой вот невозможный характер. Так, несколько парадоксально, если угодно. Вот. Но вот хорошие теории, на самом деле, для этого, я говорю, насколько нету, но это остается как такой вот проблемой. То есть, видите, идея высказана давно, и на самом деле много интересных, ну, таких развитий, что ли, в логике связано, ну, с этой статьей в том числе, и вообще с этим кругом идей. Но вот это вот, насколько я знаю, в общем, хорошей техники на сегодняшний день еще нету. Вот. Но давайте сегодня, видите, у нас такое занятие получилось, ну, как сказать, общеобразовательное, но я в этом не вижу ничего плохого. Давайте чуть два слова, вот перед тем, как мы закончим, скажу, что в следующий раз, и, собственно, я это так занятие сегодня спланировал, чтобы, ну, какой-то переход у нас был. Я вам хочу рассказать о еще одном исчислении, которое называется лямбда-исчисление, лямбда-калкулус по-английски. С греческой буковкой лямбда оно обозначается. Ну, расскажу вам, в чем дело. На самом деле это такая модель вычислений. А в том числе можно с помощью этого лямбда-калкулус тоже интерпретировать вот это исчисление задач. То есть вот эта семантика задач тоже хорошо годится для того, чтобы объяснить правила этой вычисления. И это, кстати, вот как раз говорит, вот так сказать, не синтаксически, не формально, а через семантику о такой вот глубокой связи между системой естественного вывода, интуиционистской, и вот этом лямбда-исчисления. Но с другой стороны, это как бы такой логический аспект лямбда-исчисления. А с другой стороны, можно сказать, что лямбда-исчисление – это модель вычисления. Это попытка ответить на вопрос вообще, что такое вот вычисление, что такое алгоритм. И понимаете, это как раз нас, как-то сказать, вот с этой темой тоже задач в более общем смысле и доказательств нас вот приводят тоже в сторону компьютера. Да, еще часто говорят, что это лямбда-исчисление – это самый простой язык программирования, такой какой-то, как сказать, прототип, что ли, любых языков программирования. Ну, может быть, не все тоже с этим согласятся, но что-то в этом есть. Вот, то есть наша задачка вот как-то сейчас перейти от таких чисто чего-то в области логики, да, вот чего-то чуть-чуть более практического, но не только практического, потому что вот эти задачи, ну, с одной стороны, даже вот этот Прокол говорил, что задачи, они более, так сказать, практические какой-то имеют смысл, чем теоремы, да, проблемы, чем теоремы. Ну, то есть, когда нам говорят вот построить там какой-нибудь треугольник, это кажется такой более практическим, что ли, чем там что-то доказать, даже что-то несложное, как углы равно. Но на самом деле это, не знаю, может быть, что-то в этом аргументе есть, но сейчас не в этом дело. Важно то, что, как я вам сказал, действительно проблемы, задачи играют фундаментальную роль и в сегодняшней математике. Поэтому вот нам нужно как-то, надо научиться соотносить вот нашу, собственно, логику вот с такой общей, более широкой темой, как решение задач. Ну и, в частности, вот это лямбда-исчисление. Конечно, ну, у нас много так времени уже не будет так же подробно разбираться, как вот с естественным выводом, но, по крайней мере, вот еще там пара занятий у нас будет, да, я вам что-то успею об этом рассказать. Вот, так что, ну, наверное, тогда на сегодня все, или, пожалуйста, если есть вопросы, можете мне задать. Я, в общем, много всякого вам наговорил сегодня.
Пока вроде
Ну,
бы
Евклид,
понятно.
я говорю, вот, ну, он с разных сторон интересный, но для логики, мне кажется, это тоже очень важный такой пример, что это не особенно служит хорошо как иллюстрация, там, допустим, для естественного вывода и чего-то такого, да. То есть я бы сказал, ах, смотрите, вот я вас научил формальным правилам, и тут бам. Это... Нет, оно так легко не работает. Но, с другой стороны, это вот гораздо ближе к реальной жизни, потому что оно вот и в реальной, так сказать, жизни так хорошо не работает. То есть это в этом смысле, ну, такие важные изобретения, и это важно их изучать. Но, с другой стороны, вот нельзя сказать, что тут мы всего достигли, и, так сказать, нам нужно только что-то выучить уже, и все. Вот. Хорошо. Хорошо, тогда встречаемся в следующий понедельник. Как обычно, если что-то, какие-то изменения, я обязательно пишу. Всего хорошего.
Спасибо
До свидания.
До свидания.
Спасибо большое. До свидания.
Спасибо, до свидания.
До свидания. До свидания. Да, вот.